Hello guys, in this video I'm gonna show how to program the STM32 in assembly. It's gonna be from the very beginning. It's like how to blink an LED and how to debug your program. I'd like to say that I'm not an expert and I'm doing this video as I'm learning assembly myself. So first of all, you have to have a board. You can have a blue pill. In my case, I'm gonna use this board here. It's an STM32 F47 VE. It's a really nice board. It has several peripherals already prepared. So I'm gonna use this one. But you can follow these videos with your own board. What part will you need? For now, you need documentation, and the document that you need is the reference manual. You have to download the reference manual for your specific board. Since I have a STM32 F47, I'm gonna use this reference manual. But if you're gonna use the blue pill, for example, you're gonna have to download the STM32 F103 reference manual, and in this document we have the registers of the peripherals that we're going to use. And then in software you're going to need only the STM32 Cube ID. I have created a workspace for this series, and let's start now. Let's create a new project, and then you choose your board, your microcontroller. I'm gonna choose the F07 here. Also here you can download your data sheets and your documentation here and here. So I have already these my favorites. So let's do this. Let's call this lesson 1 blink. Okay, and then here you have target project type. Let's define it as empty, and then finish. If you select STM32 Cube, it will open that interface where you can choose the peripherals, but it's all gonna be in C, so that's not the focus of this video. So let's do this. When you expand this source, you have main, syscall, and sysmem.c. Let's see what we have here. Main, we have basically nothing. We can delete this file. Okay. Syscall. Also, we have some syscalls, but let's delete this. Okay. Sysmem also, let's delete this one also. What do we have? We have a startup file. When we open this .s file, this startup.s file, we see here that this is the initialization file. This is how our board is set up, our chip is set up. And we can see here that at the end, our main function is called. So we need to create a main function. So in source, let's create a new file. Let's call it main.s. Okay. And here we need some things. Let's copy these 4 lines here. And let's paste it here. It's these are some informations to our assembler. We're saying that our syntax is unified. We are going to use the architecture, the Cortex M4, and we're going to use a soft floating point unit, and our instructions is thumb. Okay, so what do we do now? We saw that our main function is called, so our assembly needs to find a main function. So let's create a main here. And this, let's zoom in, this is how we create a function in assembly. You just give it a name. And let's do the following. Let's create a loop here. And then we can jump back to loop. What does it do? It does the following. When main is called, it goes to loop. And this B here is a instruction. It's an ARM instruction that is called branch. And then it's going to branch back to loop. So this is how we do an infinite loop. But our main function is not located. Let's try to compile this to see. We have some errors here. Let us see what I have here. Okay, the error is here. We have undefined reference to main. That is here. So it couldn't find the main function. So we have to call it here. We have to say that this function is global. So let's call it .global main. So we are informing our assembler that our function is global. So let's try to compile again and see, and then we can see that it works. Okay, let's now, we have some warnings here about those syscalls. Let's see if we can remove it if we comment this out. Let us see. Not yet. Oh, it does. Okay, so if you comment this here, libc init array, it will get rid of those warnings. So let's then try to turn on an LED. First, we have to decide which pin you are going to use. Here, I know that I have a LED in D3. An LED reference D3 is connected to PA7. And one in PA6. Let's use this PA6 here. So there are some steps that we have to do to turn on our LED. One of them is when we use @ we can comment a line. So let's use @ here. We have first to enable clock to GPIO A. Why GPIO A? Because we have PA6 and PA7 here. So GPIO A, we have to enable clock to GPIO A, and then we have to set GPIO A6 as output. So how will we do that? Okay, let us see. We can open now the reference manual, and then to enable the clock we go to RCC registers. We have here 152, and then we have to find the registers. So we go here. and then we have to find the GPIO A. So we can like search for GPIO A. Okay, then we found here, and then we can see that this peripheral reset register, what does it do? This bit is set and cleared by software, and if but one we reset IO port A, but it's not what we want to do. So let's try to find another. Then we have here another register, RCC A8B1ENR, GPIO A enable, and it's this one that we want to use. So we have to set one in this bit in this register. So we first need to get this. You can see here that we have an address offset. Why is that? It's because we have a it's how far our register is from the base. And what is the base of our register? You can see here in the beginning. Not in the beginning, the memory and architecture bus, you can see here. That is this address, 4002.3800. So let's define this base address. So we can define it here. So how we define? We use .equal, and then we use a name. Let's use RCC base, comma, and then I like to use the values in this way. So let's do this. 0x4002 to 800. This is the RCC base. Okay, and then we have to define that register that we looked. It's RCC enable. Is that right? Let's try to what is the name of the register? RCC A8B1ENR. RCC A8B1ENR. Is that right? Yep. And then what we do here, we can do the following. RCC base plus our address offset, that is 0x30. So what do we do now? Now we can enable the clock for our GPIO A. So how we do this? We can load register R0. This instruction is load register LDR. So we're gonna load the register R0 with our RCC A8B1ENR. Okay, it is going to load this address, and then we want to set the last pin. When I go back here, we want to set the last bit. So let's do this. How do we do this? We can load the value of our register in R0. What does this do? When we use these square brackets around our register, it means that we are loading in R1 the value where the address in R0 points to. So the address in R0 points to RCC A8B1ENR. Then it's going to get the value that is stored in this address. And why do we do this? Because we don't want to lose the information that is there. You only want to set bit 1 of that register. So now that we have the value, we can do the following. We can make an OR operation. This instruction here is an OR. So now we can do like an OR B1. So we're going to set only the bit 1 of this value. We can also define an alias for this, because this number doesn't tell us anything, and I like to do the following: dot equal RCC A8B1ENR, and then I gave it a name, GPIO EN. So we can do the following. What did I do here? This one will only set the first bit, so it's 1 displaced by 0. So it will be exactly this one. So let us write it here: A8B1ENR GPIO EN, and then we can start back the value. So we're going to use the instruction store. We're going to store the value of R1 in R0, but where R0 points to. So this instruction store str does the inverse. It gets the left value and stores in the right value, while the load gets the right value and stores in the left value. So that's it to enable the register, the clock. Now we have to set GPIO A as output. How do we do that? It's the same. We're going to need a base for the GPIO A. So let's also define it here: GPIO A base, comma, some value equal. We know that it's going to be another GPIO A and some things here. Let us see what we do. We do have here. Then we can come here to GPIO. You can see the registers. What does molder do? You can see here. Oh, that's right. Molder. It's exactly the first register. We're in luck. So let's define this. Molder. These bits are written by software to configure the I/O direction modes, and if we want to set the general purpose output mode, so we have to set 0, 1 for the port that we want. So if you want A6 as output, we have to set here the 13th bit as 0 and the 12 as 1. So let's do this. It's molder. It's going to be GPIO A base plus 0x00, because the offset is 0. I don't remember the value, the address of GPIO, so let's look back there. Memory map, GPIO A. What is GPIO A? is this one, 0x40020000. So it's 0x40020000. Okay. And then we have to set it as output. So let's go back there. So we have to clear this bit and set this one. So let's do this. Let's create a mask first, reset both of them, and then set only this one. So let's create a mask first. Now let's do the following. Okay, load register in R0, GPIO A molder, and then in R1 let's load the value that R0 is pointing to, and then we want to clear those bits. So let's create a mask here, GPIO molder 6 mask. We want to clear both bits. And then we displace it by 12 bits. That's it. Okay. And then to set it as output, we set only the 12th bit. Okay. So here, how we set, we can use an AND. So let's use an AND instruction here, and then AND with R1, and then we have to negate our mask. So GPIO molder 6 mask. So when we negate, all the bits are going to be 1 except these two, and when we end with that mask negated, we make sure that we are clearing these 2 bits. Okay, and then we can do an OR operation here, and here, why is okay, now it's a 6, that's right. Okay, and then we can make an OR operation here with our GPIO molder 6 output. Okay, and then we can start back R1 back where R0.2. Okay, so now our GPIO is configured. So we can now turn on, turn off our GPIO. So let's do this. We can turn on by using the bit set and reset register here. When we set the 16 first bits, we set the register, and above that we clear the register, the bit, the pin, and that register. So let's create this bit set reset. Okay, so dot equal GPIO A bit set reset register is going to be GPIO A base plus, what is the offset? 0x18. Okay. Let's try to compile and see if everything is okay up to now. And it is okay. Everything is okay. So let us see what we can do here. Inside the loop, let's do the following. Oh, I hate this. Okay, let's do the following. Let's load the address of our bit set reset. So GPIO a bit set reset register. Let's load the value in R1 that R0 is pointing to. And then, since we want to set bit 6, then we can do the following. Ignore R1 with 1 left 6, and then we can start back. Okay, store R1 back in R0. So let's yank this. What do we do if we want to clear the bits? We can do the following. So let's copy these lines and paste them down there, and then we have to when we want to clear bit 6, we have to set this bit. So let's sum 16 here. And that's it. Let's try to compile this, and it compiles. It's assembled. So let us try to debug this. Now we're going to try to debug this. So we're going to click here in debug. Then we configure our debugger, and let us see. Switch perspective. So we can see here that it stops in the main loop. So you can see also here the registers are 0. I like to show them in hexadecimal. So let us see what happens here. So we can step here. So let us do this. Let's step. We can click here to step. So we can see here that in R0 we loaded the address of associated A8B1A ENR. So step again, we're going to start now on the value that is in this register. So step, it's this one, the value. Then we're going to set bit 1, so we're going to see here. Then we can see there that it changed to 1. So when we step again, we're going to start back in associated A8B1 ENR. So it's done. Now we're going to store the value of GPIO A mode in R0. So you can see here that's for 0020000. Then we're going to start in R1 the value that is in R0. So that's it. Then we're going to clear those flags. It didn't change anything because they were already clear. And then we're going to set this one. So then it changed, and then we're going to start back. Start back. And then in BSR1, we're going to see that we're going to turn on and off our register when we go back, we go back and forth these blocks. So let us see. We can see, and then it turns on again, and then in branch loop we're going back to loop, so there, and then here the value, the LED turns off, and then it turns on. But it works. We see that it works. But what do we want? We want it to blink. Okay, so we need something to blink. So we can do the following here. We can define a label like delay that is going to do the blink for us. So how do we do this? We can say, for example, that a delay is we're going to store a value, for example, load in R0, for example, some value, like let's say 2 million, and then we're going to branch and link our delay. What does it do? You can see that this branch and link is different from this branch. What does this mean? It means that we're going to go to this loop here, and then we're going to, after it is finished, it will go back here. So at the end of this function, we're going to do the following: branch X, and then we're going to get out of there. So let us see again how it works. So let's see. And then we have to subtract this value until it reaches 0. So how do we do that? We can, for example, sub s. What does sub s do? It subtracts the value. So let's subtract the value by 1. And if it reaches 0, it sets one flag, the 0 flag. So, and then we can see what happens. We can use branch not equal to verify that if the subtraction reaches 0. So it will branch if it is not equal to 0. So it will branch somewhere. So let's create another label here, delay loop, for example. So it will branch back to delay loop, and at the end it will branch out of this loop. We can do the same after this. So let's copy this line and do the same here. Okay, let's see if it works. So, and it doesn't work. Why is that? Bx, because of this instruction. It's not only that, it's bx with the link register, because the value in the link register is the address that we're going back to. So what does it mean? When we branched and add the links here, and we came down here to delay, we set our link register, that is this LR here, to the address that we're going to go back to. So it has the address of the next instruction that we are going back. So that's it. Let's try to compile again and see if it works. And let's build this. Let's try to debug. Okay, and let's let it run free. and we can see that our LED is blinking. Okay, so I believe that's it for now. This video is already too long. And I apologize if I was not clear in some parts, but all of this is new to me because I'm still learning assembly for the ARM architecture. But I will try to make some nice projects, not to stay. I'll try to not stay on the basic. I'll try to, for example, use a display like a TFT display and develop a graphics library all in assembly. That's one of my objectives for these videos. So that's it, guys. I hope you like this. And I will upload this workspace to the GitHub, and the link will be in the description. So that's it. Thank you.